Okay, so let's talk about the first section about quantum observables. So in simple terms, this subchapter will be about measurement quantities, measurable quantities, and operators which will help us to represent those. So things to measure in quantum mechanics are represented by linear operators on the wave function space H of normalizable wave functions, and their eigenstates are the possible states of the system to be after measurement, and corresponding eigenvalues are the possible results for the measurement device. And usually we require those to be Hermitian operators, Q, with the property that it's like Hermitian conjugate basically equals to the Q. So Q star here is just like Q transposed plus complexly conjugated. But Penrose thinks that this requirement seems as too strong, so basically he wants to say that we probably should allow the eigenvalues to be complex also, not only like the real ones. And the only thing which is crucial here and which we need from them is to be the normal operators, and normal operators are defined by this equality, like Q star Q equals Q star. And if you ask why, because in that case all their eigenstates, they will be orthogonal one to each other, and therefore we will have zero probability for any of them to jump into one another right after the measurement. So yeah, and for the infinite dimensional case, we need also to assume that the set of eigenstates should also span the whole space H, which in the finite case is guaranteed by the normality. So like only for an infinite dimensional case we need that remark. Yeah, and on the next page he talks about the probabilities. So if we can try and assign probabilities to those eigenstates to be measured from some state, like some general state psi here. And striking feature is that they depend only on the quantum states before and after measurement, and not on any other property of Q, like values measured on the device or something. So for normalized states, the probability of like discovering the eigenstate phi here, in the case of the of the state of the system being like in a psi state, the probability will be equal to that like squared modulus of the scalar product of psi over phi. And for non-normalized state we also need to divide that squared modulus by the corresponding scalar products of psi and phi to normalize. And on the next page he talks about about the U and R processes, that they kind of dovetail each other perfectly because of the Schrödinger evolution unitarity. The scalar products, they always preserved in time, and so there is a guarantee that we can't ever jump with like time going on to some kind of the orthogonal state after the measurement. So in the case of superposition of two orthogonal states, where A and B are some complex numbers called amplitudes, the probabilities are just squared modulus of those amplitudes. And of course we can have like a lot more of those, like not only like two, we can combine maybe n orthogonal states or maybe even infinite number of those. So to understand that better we should talk about orthonormal basis in H. So from normality of Q and span property, which we discussed about that the eigenstates should span the whole space H, we can deduce that it possesses the family of eigenstates which forms the orthonormal basis in H. and using that we can express any wave function as their superposition, just the sum, with the corresponding amplitudes for each eigenstate, like z1, z2, z3, etc. So this process kind of reminds us about what we have seen in chapter 21 about the momentum and position states from the previous chapter. Yeah, and there we had our wave functions described as integrals, so it was like infinite dimensional continuous case. But there is the problem with those, because they do not technically form a basis, because they doesn't even belong to H, they are non-normalizable. And like quantum mechanics is full of such irritations, and if you try to be over technical, you kind of end into like what he calls rigor mortis. So basically you are like in a trap and you can't get anything done if you're getting too technical. But and therefore you need to kind of steer a middle path there between the mathematical rigidity and general sloppiness in the ideas, and that's kind of life with which we need to deal with. Yeah, so basically that's it for this subchapter. Maybe you have some questions about this or something to add?
I've never really been fully sure why the things we measure have to be eigenvectors of the observable that we're measuring. I don't know if there's like an easy way to explain that.
Like,
I've always just heard it taken as like an axiom that anytime you measure something, it has to be an eigenvector.
yeah, for me it's just axiom currently, so like I don't know why actually, like from like practical.
Well, if you're measuring it, what you're getting out would be an eigenvalue. So you wouldn't get that value, a single value, if you weren't in an eigenstate, right?
Mm-hmm. So you're measuring the values, that's true, and the system jumps to the eigenstate. Yeah.
Right. Yeah. I'm honestly still a bit puzzled by that, but I don't know. I guess I can just take it as an axiom for now.
I think that we should assume that, and maybe later, when we will discuss more like philosophical aspects of that, or we will understand more. I think. I hope so.
Yeah. The only other thing is, this is the first time I've heard of people letting like the operators be non-Hermitian, like so that you can get complex eigenvalues. This is sort of a new concept to me, but I guess we can run with it.
Yeah, I think that's like Penrose's own views on that theme, and I think he is like really big lover of complex numbers, and therefore he just don't want to dismiss the opportunity to use those as the something we could measure. So I think that's it. Okay, so in the next subchapter, he is talking about yes/no measurements and the projectors, and the motivation for it is the fact that for non-normalizable eigenstates, like for the X or P observables, the probability to measure some fixed value for the quantity is always equals to 0, because of their like continuity basically. And so we might prefer other kind of observable here, the one which asks if the value lies in some boundaries or it is not, and those kind of measurements are done a lot in quantum mechanics and are one of the most basic things to be asked about the system. And the observable of that kind is described by the projection operator, and its property described by that equation, like e squared. Basically, if you project twice, it's the same if you project only once. And also it should be Hermitian. And problem with those is that in dimension bigger than 2, these are thoroughly degenerate, and that means having more than one dimensional eigenspace for at least one eigenvalue. So in from practical perspective, it means that for some measured value q, we won't be able to tell to which of the eigenstates our quantum mechanical system has jumped, because our eigenspace now is more dimensional, and it has a lot of vectors inside. And this issue is resolved by postulating the projection postulate, and it states that the state psi subjected to the measurement is projected orthogonally by it to the corresponding eigenspace of the observable. So for any such degenerate Q, we can form the new observable E, which just equals to the equation is the result of Q measurement equals to Q small. So Q eigenspace for Q now becomes like E eigenspace for 1 in that case. And this E will be a projector operator, and our projection postulate just will mean that our state psi will just jump to the E psi here. And we can also kind of divide the whole space of the resulting wave functions into two, by using the other operator, which equals I minus E here, and therefore we can kind of describe our original wave function as the superposition of two orthogonal states, and they will be E psi and I minus E psi. So you can check if you will try to take a scalar product of those, you will find out that it equals to 0. So basically you have two orthogonal states, and our system after E measurement will just fall into one of those. Yeah, and geometrically it could be represented using this picture below. So basically we just have two subspaces with yes and no answer. Our psi lies in some bigger space, and we, after measurement, just perpendicularly projecting our original state to one of these subspaces, yes or no. So that's the basic theory behind the projection postulate here. Any questions about this? Yeah, it's pretty tricky thing. I was amazed that practically having bigger eigenspace means that we cannot tell exactly in what quantum state our system is after measurements. So it's a really tricky thing to have that projection postulate. And actually in the next subchapter, Penrose will try to show us some examples and why do we need that. So basically in the next subchapter he starts from the paragraph saying that some physicists are expressing the doubts about the projection postulate as unnecessary or unobservable, and because of the difficulties to determine what the state has actually become after measurement. And that indeed is a complicated issue. Penrose agrees with that, but still we can have good examples where projection postulate nicely describes the non-adapted measurement. So, but to understand that, we need to consider what null measurements are, and in other words we could call those interaction-free ones. And he starts from the example already familiar to us from chapter 21, actually 21.7, but now he has the detector trying to catch one part of the original photon. So basically we have a source here, we have some kind of a silver mirror or something which will reflect part of the wave function into one direction and will transmit other part forward, and we just place in that detector on the right here to trying to catch the tau part. So like the wave function state in this case is like tau plus r, and the remarkable thing is that the measurement of non-detection of the photon has caused the photon state to undergo a quantum jump to r or rho automatically, despite the fact that the photon has not interacted with the measuring apparatus at all. And of course, we need to assume in that case that our source and our detector are like perfect ones, so we are kind of 100% sure that photon was emitted and that it wasn't catched at the detector. So it's kind of, as far as I understand, it's kind of idealistic situation, but it's allowable in terms of like thought experiment or something. Yeah, so basically what we have here that like non-detection guarantees the collapse of the wave function to the raw state. And now we can take a look at more elaborate one example, and the next example is called Elitzur-Weidmann bomb test, where we have a Mach-Zehnder type of setup, which we've seen in chapter 21 already, with A and B detectors. Placed the same way as in Mach-Zehnder type experiment, but now we have intermediate detector C, which could activate the bomb if it detects the photon here. Yeah, and we want to ascertain presence of detector C when it doesn't catch the photon, so when bomb hasn't exploded. And we can do that by observing the photon on the detector B in this case with probability 1/2. And why could that happen? Because after non-detection by C, so bomb hasn't exploded, right? It is guaranteed that it took another pass and there is no interference now at the final mirror, and therefore that part of the photon after the collapse done by non-measurement at C, it will just go through that left hand pass, and just like one part of the wave function will hit the final mirror. It will be split like in two, and therefore with probability 1/2 it will reach A or B. And at the original setup, because of the interference, it could reach only A detector. So we can kind of find out the presence of detector C even now, even if we do not know exactly if it was like present. So just by having the observation at the B detector. Yeah, and now we're kind of ready to illustrate the point made about the projection postulate, but we need one more degree of freedom to add to use that. So we need to consider for this the photon polarization, which is quantum mechanical spin in a massless particle case. So let's add it to the mix. And then on page 547, Penrose talks about the spin, like in basic terms, and he says that the amount of spin, like that modulus or absolute value of S is always the same, and it could be right-handed if S is greater than 0, or left-handed if S is lesser than 0. Yeah, and also spin can be any superposition of those two basic states, which you can see on the picture. Yeah, and S quantity is called helicity of the particle, and it is a half integer or integer. And in the case of photons circular polarization, S equals to plus or minus 1, and plane polarization is just some combination of those circular polarizations. And all we need to know now is the fact that polarization switches to the opposite helicity for the reflected part of a function and is preserved for the transmitted one. So now we can go back to the first experiment described in this subchapter and add helicity to it. So we are assuming that source is producing photons with positive helicity, right-handed one, and we aim the source almost perpendicular to the mirror, so it will have the reflected part going like almost in the same line with tau plus, as you can see on the picture. Yeah, and we also have the same detector placed on the right here to catch tau plus part here. So by assuming this fact that polarization switches, we now know that like the psi plus state of the system after encountering the mirror could be represented as a superposition of tau plus rho minus here. So reflected part of the wave function changed its helicity. And now by getting null on the detector, we are collapsing the wave function to the r minus 1, rho minus 1. And the point is that the full projection postulate is needed here to discover this fact. Because like there is a degeneracy for both these alternatives, because the eigenspace of no answer is the two space spanned by the rho minus and rho plus, and eigenspace for the yes answer spanned by tau minus and tau plus. And in this case we need the projection postulate because it correctly carries us exactly to rho minus in the case of no measurement here at the detector, rather than to the rho minus or rho plus or any other linear combination of these. So that's kind of the example which Penrose uses to demonstrate the need in the projection postulate. So in this basic setup, we needed to guarantee that after measurement our system will be in rho minus state, and it's kind of how to say it, like is fundated or based on the the theoretical properties of spin and helicity here. Yeah, the chapter actually also included something about the projective spaces and Hilbert spaces, but like that material seemed a bit tough to me, so and probably not really useful here. So I just haven't included that into the notes. So, but if you have something to add about this or you have any questions, please tell.
Well, there was one thing that sort of bugged me here, and that was like for the spin one, you can either have it up or down, like along the axis that you measure it. But if you measure it like on a perpendicular axis, it could be 0, right? So say it's in spin up along the z-axis. If you measure it along x, then it would have 0 projection along x.
Mm-hmm, mm-hmm.
So it's interesting that he only included the plus or minus and not the 0 state here.
But like,
because I know for the case of like spin half,
mm-hmm.
The projection onto like any axis would be 1/2. But for spin one, it could purely be along z, and then if you measure it along x, the s would be 0.
But like in this case, we're not measuring it along the other axis, right? So we just measuring along one axis ideally, and that's it.
Yeah, I mean, he does talk about these combinations of spin up and spin down, and that's how you can write those like total spin zero states. But I'm surprised that he hasn't worked with the combinations in this section here.
But like for example, you can see the state, like wave function state on the screen here, this picture. Uh, how will that change if you include some combinations here?
Well, I think that plus sign between the tau and rho states, I think the plus sign would just become a minus sign. That would give you like a spin zero state. They also call it a Bell state.
Mm-hmm, mm-hmm. Yeah, maybe like that's because we haven't talked yet about spin too much, and also because we haven't talked about the entanglement and Bell states yet. So maybe he had some reasons not to include those here.
Yeah, true. I think that the example that he plays out it shows up more effectively with a spin half instead of a spin one. But he's about to go into spin half anyway.
Mm-hmm, mm-hmm. Yeah. Anyway, like I'm not expert.
I had the same question when I was reading. I don't know.
Could you repeat, please?
Just saying that as I was reading, I was trying to figure the same thing that Joe's asking about. I was beating myself up about too, and I never quite reconciled whatever's happening. Because, like you said, it seems like he's doing a spin half quantum angular momentum thing is what he's setting up, but he's calling it spin one. But it doesn't seem to be behaving like a spin one. But I don't know. Maybe, hopefully, it's not important.
Yeah. Like me myself, I'm not a big expert in those matters, so I just was believing him here. But like maybe he got some some mistake here. I don't know. So
Well, so he was right to say that the absolute value of spin will always be one. And that you could project that like either along the axis that you measure it or opposite the axis that you measure it. But there's a third option, and that's that it's perpendicular to the axis of measurement. So that would be the zero state. But that doesn't end up being the case for spin half. I don't think that he got to any wrong conclusions. I was just kind of surprised that he didn't include the zero state.
yeah. I'm just not sure what is it. So I'm not sure I got it. So you're talking like it's a bad scene that I cannot draw on my screen. So I'm imagining those states about which like he been talking about here, like the plane polarization, for example. It's like a circle on a plane, right? And like a combination of two variants, like spin down or spin top or something, right?
Yeah, I think he shows it better in that figure that's just above here, with parts A and B. So like spin up would be the one that's like right-handed, and spin down would be the one that's left-handed. But you could just as easily have pointed the spin along the x direction. If its direction of motion is on z, the spin could point along x, and it wouldn't be right or left-handed. It would be like longitudinal.
Like if you just rotate the system, basically.
Yeah, and so I mean, A and B here are definitely like valid states for the system. There just seems to be a third one that's missing.
And the third one will be like when particle flies and that circle goes like parallelly to the direction of something.
Yeah, so it would be like some component of it points along the z direction, and then the other component of it points against the z direction. And ultimately, that would be like a spin that points along x or y, or just anywhere in the xy plane.
Okay, maybe we will got more information about that later. Once again, so I assume we can kind of leave that as is for now and continue to the next subchapter.
I wanted to mention one thing just quickly. I can't remember if it's in this book or not, but I came across something called Jones calculus for optics. I don't know if you've heard of it. I think it's like a classical optics theory, but it represents states using complex vectors, and you can sort of change the state of vectors using matrix operators. So I just thought it was interesting because even though I think it is a classical theory, it still has a very sort of quantum flavor to it with these state vectors and these sort of matrix operators. So we don't have to go into it now, but I thought people might be interested to know about that.
Totally. Thanks for bringing this up, Slava. Could you scroll up just a little bit? There was another table here. Yeah. So these, see how we have these states with the minus signs in there? The linear polarization states with the minus sign, and then the like minus I in there as well. A and R. These are the states that are left out. So I'm surprised by it because like you see that the state space is still two-dimensional. It's either spin up or spin down, but the combinations of them give you more states, and you only get a two-dimensional space if you project it onto like a single axis. Yeah, we don't have to dive too deeply in here, but I just wanted to point out these the states with the differences on them are. These were the things that I'm talking about. Like you can assign these to like spin along X or spin along Y, and they're neither spin up or spin down.
Yeah, it seems to me I've seen something like that, like in other books when you kind of deduce the poly matrices or something, you kind of come with those different spin states like up, down, left, right, and like to you and from you or something, right? And they will represent it by those different linear combinations like R and L here.
I'm just really quickly looking, in forums, and I'm finding that it's just because photons are massless. When we say spin, it does not really mean the same thing as the spin of a massive particle. And the really mathy stuff that I don't quite understand, I need to look into it more, doesn't work. So when we say spin of a photon, what we really should be saying is talking about helicity, because it's not the same as spin when we talk about other massive particle spins.
I think I see what you're saying. It still bugs me that the spin could be pointed along X, and it's moved at the speed of light along Z. So the projection of the spin onto the direction of motion is still zero. So I get what you're saying. It still bugs me.
Okay, so let's continue and talk a little bit more about spin. Maybe add something like more confusing to that matter. Okay, so the next subchapter starts from reminding us that in previous chapters we've seen that time translations give us like energy conservation, and space translations give us momentum conservation. So and in the same way we have like the rotations, they give us the angular momentum conservation. And here Penrose like explicitly says that for a massive particle we can imagine being in its reference frame, and so its rotation symmetries could be represented as the O3 group here. I was a bit surprised because I was thinking about SO3 group. So I had a question here, like why he could use like reflections also here, the other part of O3. But probably it just doesn't matters, because in the next paragraph he just says that angular momentum components in quantum mechanics, they live in Lie algebra of O3 or SO3. So Lie algebra doesn't distinguish between those. Basically O3 and SO3 Lie algebras are the same, and the elements of that Lie algebra are just infinitesimal rotations. And we know that like SO3 elements, they do not commute, and therefore Lie algebra generators L1, L2 and L3, they do not commute also, which is stated by those equations here. And therefore for the corresponding angular momentum components we have the next anti-commutation relations, like in the similar way. It's kind of it could remind you about X and P commutation relations, where we have like IH and delta function here, or like Kronecker delta or something. But now instead we have L3 or L1 for L2 and L3 here, so they're kind of self-connected or something. Yeah, so and quantum systems possessing angular momentum, they provide a representation of the algebra of SO3 in terms of linear transformations of our space of wave functions H here. And one of those is two-dimensional representation in terms of the Pauli matrices, or Pauli matrices, and in that representation we have L1 described as Z matrix, L2 with ice and minus here, and L3 is like 1 and minus 1 on the diagonal. And here my summary notes ends, so we can jump to the book directly. Yeah, so they provide the simplest non-trivial representation for the angular momentum, and we can imagine that these 2x2 matrices act on a wave function with two components, psi0 and psi1 here, and when we start to rotate this state, the components get turned around in accordance to those matrices, and we can label that two-component wave function as psi a here with a lower index a, which takes values 0 and 1, or else we can think of this as an abstract index according to the abstract index notation. And that quantity described by psi a is called a spinor, and right, spinor or spinor? Spinor, okay, called a spinor, and its index a is referred to as 2-spinor index. It turns out that psi a is indeed a spinorial object in the sense described in chapter 11. So if we rotate it over 2 pi, we find that it will change its sign. So, and we can confirm that if we continuously exponentiate one of the Pauli matrices until we get an entire rotation through 2 pi, and we'll find that we are obtaining the operator minus I, which actually gives us a minus for our wave function or spinor here. Yeah, and basically afterwards he's talking that like that notation in spinor formalism can actually replace tensor calculus or vector calculus here. So like in some sense spinors, they're kind of more general entity or more basic entity, and for example like 4 vector could be described using 2 spinors. Yeah, and he talks here about van der Waarden notation, about those indices like that we could have like n spinor things with a lot of indices. Some of those could be primed, some could be unprimed, but and those primed and unprimed are like complex conjugate of one another, but we will not need those soon, so we just will talk about that notation later. And also at that bottom paragraph here he talks that he will assume as for now and probably for all later chapters when it's not needed, that like we have Planck units here in which h bar equals to 1, and he says that we can also always go back and kind of revive the h bar back if we need, so we shouldn't be worried about that. And now we can return to the 2 spinor formalism, and we recall that quantity psi a here can be used to describe a particle of spin 1/2. Yeah, and he says that, but I still have a why question here, so he hasn't explained actually why why it is it describes the particle spin 1/2. He haven't said anything about that before, so at that moment I just believed him. And the same kind of notation can be adapted for higher values for the spin of the spin corresponding to other representations of the Lie algebra of SO3. And the value of spin is always a non-negative integer multiple of 1/2, like one number among these, like 5/2 for example, or 4/2, which equals to 2. So yeah, and if we used h bar here, then we should include like h bar multiplied by that value here. Yeah, and anyway, the wave function now can be described by an object psi with those capital indexes a, b, f here, called spin tensor here, which is completely symmetric in its n indices in the case of spin n/2. And yeah, and he is saying here also that in fact all representations of SO3 where we include the 2-valued spinorial ones can be built up as direct sums of these particular ones, the irreducible representations. So this amounts to saying that the general representation can be expressed as possibly infinite collection of the wave functions with different like spin tensors here, each of which is totally symmetric in spinor indices. Yeah, and for individual particle there would be only one such symmetric field, our psi ABF here for its wave function, and it would be an understandable mistake to think that for the 2 particles there would be 2 of them separately, for 3 particles 3 of them, and we shall be seeing how systems of more than 1 particle are actually described in the next chapter. It is something distinctly more subtle than this, and for a spin 0 particle called scalar particles such as p meson, this wave function has 0 indices, and this was the situation treated in chapter 21. Probably when we just had some kind of the function and that's it. And like, so our psi hasn't any indices there. Okay, and the most familiar particles like electrons, muons, neutrinos, protons, neutrons, and also their constituent quarks all have spin 1/2. So just one index here. And the deuteron, nucleus of heavy hydrogen, and the W boson, as we will see in chapter 25, have spin 1. So they will have two symmetric spinor indices, and many heavier nuclei or even whole atoms can be treated like single particles with much higher spin. For spin n/2, the n-index object has n plus 1 independent complex components. Okay. And also the spin tensor is frequently referred as an index spinor. It is a spinorial object only when n is odd. These being the cases where the spin is half-odd integral, not integral. And it should be remarked also that spin value itself, labeled j here, equals n/2, determines and is determined by the eigenvalue j multiplied by j plus 1 of the total spin operator, and total spin operator, that j capital here squared, is just equal to the all of our angular momentum squared and added together. And that total spin operator g squared commutes with each component or like with each generator of the infinitesimal rotations in our algebra of SO3. And this property characterizes g squared as a Casimir operator or Casimir element for SO3 Lie algebra. And to delineate quantum states completely, we usually form a complete set of commuting operators, as we will see in subchapter 12 of chapter 22. And we look for the states that are simultaneously eigenstates of all the operators of the set. Okay, and for angular momentum, this is normally done by taking the operator L3 of angular momentum about the z direction and accompany it with g squared. So in that case we will have like two quantum numbers called j and m to label these states. So in that case, j by j plus 1 is the eigenvalue for g squared, and m will be the eigenvalue of L3 here. And we take j greater or equal than 0, and m in boundaries from minus j to j here, where j and m are both half-odd integers in the spinorial case, or both integers. Okay, and 2j plus 1 or n plus 1 different possible m values correspond to the different components of the spinor tensor here. And actually I assume that in the 22.12 we will discover the ladder operators which will give us those eigenstates and eigenumbers going from minus j to j here, just like they will kind of allow us to go up and down between those, and probably we will kind of see exactly what those mean. Okay, and actually the book, I think we've been talking about that book a few chapters ago, called Physics from Symmetry by Jacob, I forgot his surname, like Schwichtenberg or something. Yeah, so basically in that book he nicely describes that process of like forming the Casimir operator and like deducing different representations for SO3 group or SU2, probably SU2. Yeah, and SU2 is just like a double cover for the SO3. So yeah, basically like the algebra probably in that case they will just be the same. And he's talking about SU2s are. He also taking that operator, and he has like a general scheme describing their ladder operators in details and how different like spins will lead us and like to different representations or something, and also different dimensionality will give us like different J values here for the Casimir elements. There is a result called Schur lemma, which can associate with that Casimir element the corresponding number different for the different dimensions in representation. Like something, for example, like in 2 dimensions it will be like something like 3 over 4 or something like that, and like for 3 dimensions it will be like some other number, and those numbers will kind of characterize the spin value accessible or something. So actually, if you want to know more, I advise you to take a look at the at that book shared in one of the Discord channels called Physics from Symmetry, and it has really nice descriptions of that process. Okay, and yeah, question?
There's also another way to find these J and M values, and that's by solving differential equations. So what happens is like there's a couple of differential equations that just come up from trying to solve the Schrodinger equation, and the solutions to those diverge if you end up like taking all the terms. So you end up having to like cut off the solutions at particular values, and that's what gives you these J and M. Like I don't think that Penrose will actually go through it in this way, because there's multiple ways to recover these. But you can actually get them just from differential equations and having to like cut off a series.
Yeah, interesting, because like as far as I remember, as far as I recall, like different spin values will correspond to like different representations, right, of our like SO3.
Right. So the equations that I'm thinking of are like the Legendre differential equation, or like the Hermite differential equation. These are things where you end up having to like cut off the solution to it, and you end up with these integers or half integers. Yeah, so see, they do a series solution, and you can see we end up with like L and N in there. That's actually what we're using as L or J and M.
Yeah, but
and so they ended by saying the series has to be cut there.
Yeah, at the end here. Yeah, it would be interesting to see those used in the case of the J and M, like connected to the physical situation.
Just a quick note.
I think they come up with the solutions.
Yeah?
No, please go ahead.
Yeah, Joe, please continue.
I think they come up with the solutions for like the Schrodinger equation when you set up the hydrogen atom. You end up with these differential equations. Basically, the one at the top is what you end up with. But rather than putting it as L times L plus 1, they use alpha. And they ultimately come down to say like, oh, well, alpha must be an integer times the next integer. So that's why they put it in there like that, L times L plus 1. Because at least in this setup, it's just a constant.
Not Poisson, not Poincaré. I just wanted to say that in the book, like Physics from Symmetry, author is using the property that the Poincaré group acting on the Minkowski spacetime could be represented as like two copies of SU2, and therefore you kinda can describe all of the irreducible representations of the Poincaré group acting on spacetime using like two numbers and like a pair of numbers, each one corresponding to different SU2 part of the Poincaré group. And therefore you will be obtaining something like 0-0 representations, like 1/2 0 and 0 1/2, and those will give you like left-handed and right-handed spinors, and afterwards you'll have 1/2 1/2 representation, and if I'm recalling correctly, it will give you like 4 vectors, and you will see that you can kinda represent the 4 vector as 2 spinors or something. So basically you will find out using those that like Lie algebra theory that spinors, they're kind of more basic things even for the space-time than the 4 vectors, and that's kind of like amazing or interesting fact for me personally. Yeah, and Alex wanted to say something, or?
Yes, just a note about this Casimir. I just maybe wonder if this is somehow related to the Casimir effect. If people are familiar with that. It's the same person who discovered the Casimir effect.
I don't know, but I bet that it's just his name used differently, like for 2 different things.
Maybe, but it's the same Casimir at least.
Yeah, we need to fact check that. I don't know.
Oh, I just checked it. It's the same Hendrik Casimir.
Okay, great. Then we know already. Thank you. Yeah, and so we have only like the last paragraph here, which says that the choice of the upward direction is of course arbitrary, and it corresponds to choosing up-down basis, which we will see in the next subchapter for these spinor components, and any other special direction could equally well be chosen in place of up, like left or right, as we have said already. And accordingly, I shall occasionally refer to the m value in some other given direction, as with the Majorana description. And m value is the eigenvalue of L3. Okay, so still I think that like we will understand a lot more when we will reach to the end of that chapter, because like me personally, I do not exactly understand what is happening here. If someone can help me and describe what's happening with that complete set of commuting operators, then please do. So I know that we are kind of using G squared and L3 here, but like I'm not sure why it is a complete set. I know that they commute, but why that set is complete in some sense?
Well, I think you can consider like just linear algebra with this. Like, you can form a vector space given n basis vectors. Let's work in 3D. So if you have 3 basis vectors, that gives you sort of like the columns of your identity matrix, right? 1, 0, 0, 0, 1, 0, and 0, 0, 1. That gives you your basis for the space, and you know, if you put those three vectors together as a matrix, it's the identity. Now, any matrix that you could get from doing like the elementary row operations, you know, like scaling a row, or you know, switching the two rows, or there's you know, a variety of different matrices that you could get from doing elementary row operations on the identity, and those all have the same eigenbasis. Like that basis will be the same for the identity matrix and all of the matrices that you can get from doing row operations on the identity. And so I think that's what they mean by what do they say? Simultaneously diagonalizable? Oh, no. They say complete set of commuting operators. So just the fact that they commute means like that they can all be like reduced down to the identity matrix. And I think the elementary row operations do commute. So it's kind of like a strong like linear algebra point of like, as long as they share the same basis, then they can be like simultaneously diagonalized.
So, like, it's just strange for me that like L1, L2, and L3 in this case, they're kind of the generators of Lie algebra, but they're not commuting between themselves, and we can form like G squared, which commutes with every element. And if you take like G squared and L3, then any other operator constructed from generators will commute with G squared, and which commutes with both of those, gives nothing new, since it must itself be a function of these two.
So this is what I'm talking about with like doing the row operations, is you just put together these matrices for J squared and L3. And then if you do any sort of like elementary row operations, things that like preserve the determinant, as long as you do like any of those sorts of operations, you'll have the same basis.
So basically you'll have the same set of their like eigenstates, right?
Right.
And maybe commuting properties somehow connected with what could be measured like simultaneously or something like together. I'm just thinking.
Yeah, I think that's right, because these are projective measurements. So if you project onto one basis and you want to project onto another basis, you'll lose information if they're not the same basis. So these operators need to share the same basis in order to like not lose any information between like measuring one and measuring the other.
Yeah, so he's talking here in the next paragraph about that. Like, we need commuting observables, and the reason for that is that in that case we can label states with two eigenvalues here for A and B.
Yeah, so he forms a family of basis states, and they have eigenvalues for each one of these operators, but they're all the same basis. And that's what they mean by like the simultaneous diagonalization.
Yeah. So it seems that the answers to my questions lies in subchapter 12 here. and like that means that that's okay for now not to understand everything. So it was just a hint about the Casimir operator, and we will talk more about that later. Okay, so I propose to finish for today at this place, and for the next time we will try to read like 3 or 4 subchapters more.
Yeah, that sounds good to me.
Yeah, I think probably to 22.11 including it, and optionally the 12th one if we will have like more time and we'll manage to read more. But I think that like 9, 10 and 11 will be enough. There is a lot of information there.
Yeah, and I think that a lot of these things are really hard to see just by reading it. I think that, sometimes you just gotta like work out